Hello student, welcome back to lecture series on Z transform. For more videos you can check in my I button here, so you will get the more videos in my I button. I uploaded plenty of the videos based on the Z transform and Fourier transform. Okay, so in my today's video I'm gonna explain to you all definition of a Z transform with some of the examples. Okay, so without further ado, let's get dive into our today's lecture. We're gonna see first of all what is the mean by Z transform. Okay, so actually Z transform is the sequence of f of k. Okay, yes, let me write the definition. What is the mean by Z transform? Okay, actually Z transform is the sequence Z transform is the sequence of f of k. Okay, so we write function like this one is the sequence of f of k. Okay, that means I already explained what is the mean by sequence in my last lecture. Okay, yes, Z transform is the sequence. It is the sequence for that f of k. Okay, and we denote this. Okay, we denoted as, okay, we denoted as Z of f of k. Okay, this one is the way we denote Z transform, like a Z of f of k. Okay, and Z of f of k, and we define Z of f of k sequence. Okay, Z transform, we define Z of f of k. Be careful, this one is important, guys. Okay, this definition I'm going to apply everywhere. Okay, so Z of f of k, the definition can be written as, or we can write this one as capital F of Z. Okay, so this way we can also represent. Okay, this is just the representation of Z transform as f of Z, or you can define Z of f of k. Okay, actually this is the sequence f of k. Okay, for our Z transform, and we write summation. Already explained, I explained in my lecture what is meant by summation series. Okay, yes, and summation it running from, we consider here negative value to up to the positive value. Okay, so summation running from minus infinity to plus infinity. Okay, f of k. Okay, f of k Z raised to minus k. Okay, okay, now see that f of k Z raised to minus k, or we can write this one. You can take that negative power to the denominator also. Okay, so we write that Z transform as a k running from minus infinity. Okay, this one is a negative of infinity to the positive of infinity. Okay, k is equal to negative of infinity to positive infinity, f of k. Okay, f of k upon Z raised to k. Okay, this one is our required Z transform. Okay, so mostly we are going to apply this over here. Okay, this result, actually this is the definition for Z transform, guys, not the difficult. You need to remember what is this. Okay, this one formula. Okay, so we are going to prove most of the result using this Z transform. Okay, yes, and what is the Z here? Okay, let me explain what is the Z here. Small z can be written as x plus iy. Okay, small z can be written as x plus iy here. Okay, actually as we are looking through complex number. Okay, yes, so z represent x plus iy. Okay, and Z is a Z transform. Okay, this one is a Z transform. This one is a Z transform. Okay, for our sequence f of k. Yes, okay, so we go for adding some results. Okay, using the Z transform. Let me show some result here. Okay, you can see that I added that definition here. Okay, so Z transform of f of k which exists if sum of a series on RHS exists. Okay, Z transform when it is exists, when that sum, it is a series sum now, that is sum, it is coming later on. If that exists, then we write Z transform of f of k exists. That is only. Okay, that means if that series exists, that means we write it is convergence. Okay, it is a convergent, but as we have series, so we write convergent, absolutely convergent. Okay, but in the real analysis, when it is modulus convergent, then we write is absolute convergent. Okay, convergent. But as we have f of k upon z raised to k, so we consider it's other than modulus. Okay, we consider as a Z transform. Okay, we consider as a Z transform. So we write, if this series exists, we write this converges absolutely. Okay, yes. So casual sequence means we consider only the positive sequence, guys. Okay, so one more definition: casual sequence. What is the mean by casual sequence? Whenever we have series which running from 0 to infinity. Now see that already we learned series can run from minus to infinity in the case of Z transform. But when we have sequence as a casual sequence, so we consider instead of a minus infinity from 0. Okay, so we write in series from 0 to infinity as a casual sequence, f of k z raised to minus k. Okay, so this one is our casual sequence. I hope you all have understood the definition for casual sequence. Okay, actually it is only the positive number in our series. Okay, yes, that is only. So we go for solving some of the standard sequences. Okay, we go for solving some standard sequences using this Z transform. Okay, we see standard sequences. Okay, so already you all are learned, okay, to solving discrete valued function. Okay, we use Z transform. Okay, like a f of k, sequence of f of k. Now we have sequence of f of k. Okay, sequence of f of k. We use to solve that sequence of f of k Z transform. We solve that sequence of f of k using Z transform, and we land on the f of z. Okay, like it is a Z transform. Okay, so we use that f of sequence of f of k using Z transform. Okay, and actually that sequence of f of k, it is the discrete valued function, discrete. Okay, discrete valued function. Okay, this one is actually discrete valued function. We apply on a discrete valued function Z transform. Okay, so we get the f of z here. That is only we find here in our sequence. Okay, yes, let's go for solving some standard sequences. Okay, standard sequences, plus we go for adding some examples based on this, guys. Okay, it is way easier, not the difficult. Okay, so first sequence we are going to prove here. First sequence we go for, we have standard results, some standard sequence. Let me write the standard sequence here. Okay, it may sum some standard sequence. Okay, yes, sequences, we are going to take more sequences over here, some standard sequences. So we write our first sequence as a Z transform over. Okay, we take sequence a raised to k. Okay, so already I explained how sequence running in my last lecture, and k running from k greater than 0. Okay, so this one is our sequence. Okay, so I have to prove some short result for this standard sequence. Okay, so in most of the case you don't have to calculate the same terms again and again. It's time taking in your question paper. So mostly, so we use this result for finding the Z transforms. Okay, yes, and we can write this sequence as a Z upon Z minus a. We write this sequence as a Z upon Z minus a, and modulus of a Z is greater than modulus of a. Okay, modulus of a Z, it is greater than modulus of a. This one is a standard sequence. Yes, so what we do now, we go for proving this sequence using Z transform. Now see that, guys, it is way easier. So we just have to apply the definition for Fourier Z transform. Okay, so what is the definition for Z transform? We write Z transform. Okay, we write Z transform over f of k as a k running from minus infinity to plus infinity. Okay, this is the summation f of k. Okay, this one is f of k and z raised to minus k. Okay, this one is our standard definition for z transform. Now see that I'm going to apply this definition to our first standard sequence. Okay, this one is the first. We are going to prove some other ones also. Okay, so now we are going to prove this one. Now see that if you compare this result, now consider this side, prove this side. Okay, so you have to consider this side over here. Okay, so we don't have till inverse z transform, that's why we are not going to consider this one. Okay, so we have only the choice which we need to opt, okay, as a z into z of a raised to k. So consider this side, substitute here and find out the sequence using this and prove this one. Okay, yes. Now see that z transform over a raised to k and z transform over f of k. Okay, that means what is the value for f of k? As a raised to k. Okay, so f of k we write as a raised to k after comparison. Okay, yes. Now put it here, z transform over a raised to k, and we have condition k need to be bigger than 0. K need to be bigger than 0. That means we don't need the value from negative infinity to the minus 1. Okay, so we consider the value which including 0 to positive infinity. So we write value running from k running from 0 to infinity. Okay, k running from 0 to infinity. What is the f of k? Is a raised to k. Okay, replace a raised to k here and z raised to minus k, z raised to minus k over here. Okay, yes. So as we have to expand that series here. Okay, as we have series running from 0 to infinity, that means put 0 plus put 1 plus put 2 plus 3 and plus so on. Okay, so see that how I am going to define that sequence over here. Okay, so k is equal to 0. So a to the power 0 means any number to the power 0 gives us the 1. Z to the power 0 it also gives 1. So first number it goes to the completely 1 plus. Second, after 0 we write 1. So a raised to 1 plus z raised to minus 1. Okay, so a into z raised to minus 1 plus after 2 a square z raised to minus 2, a square z raised to minus 2 plus, okay, plus a cube z raised to minus 3 plus a raised to 4 z raised to minus 4 plus a raised to 5 z raised to minus 5 plus so on. Okay, now see that this one is actually the expansion for our given summation. Okay, yes. Now see that this it looks like geometric series. Okay, all the terms are similar here with their common differences. First term it is the same. Okay, so if you're going to take common difference everywhere, you will get it same. Okay, so we gonna go for the writing as some specific form, 1 plus a into z raised to minus 1. Okay, a into z raised to minus 1. Okay, plus take 2 common from the bracket, a z raised to minus 1 to the power 2 plus take 3 common from the bracket, a into z raised to minus 1 to the power 3. Okay, yes, plus a into z raised to minus 1 to the power 4. Okay, plus so on. See that guys, what I have done, I taken that 2 common from this one. So if you multiply under 2 or take power inside the bracket, we write a square z raised to minus 2. That means this power 3 it is for a also and z also, power a also z also. These are the basic concept you need to know. Okay, yes. Now see that this sequence, this series, it's represent some geometric progression. Okay, now see that geometric progression for 1 plus x square plus x cube plus infinitely many terms. Okay, so we write 1 upon 1 minus x. Okay, 1 upon 1 minus x as a 1 plus x square plus x cube plus so on. This one is the expansion for this term now. So already we learned which is equal to 1 minus x raised to minus 1. Okay, this one is the expansion for this term. Okay, now see that what we have 1 as it is here. What is the value for x? A into z raised to minus 1, a z raised to minus 1, and it's x again, power 2 as it is there, power 3 as it is there, x as a into z raised to minus 1. Okay, so we compare this one and we write this one. Okay, so we write entire step after this. This is the result we are going to apply. Okay, so after this I'm going to write as 1 minus x, a into z raised to minus 1. Okay, a into z raised to minus 1 to the power minus 1. Okay, So what I have done, see that 1 minus x is a into z raised to minus 1 as it is here, minus as it is here, negative power as it is here. I compare the two sides here. Okay, yes, let's go for the next step. I'm gonna explain here to the next page here. Okay, so as we have here power 1, take to the denominator, so 1 upon a minus az raised to minus 1 remaining. Okay, so we write this one as a 1 upon 1 minus az. Okay, 1 upon 1 minus az raised to minus 1. Okay, this one is the actually term. Okay, so that negative power I taken into the denominator here, so z raised to minus 1 also take as a 1 upon z. Okay, so we write 1 upon, we write next step 1 upon 1 minus a upon z. Okay, so this multiplied by this minus this divided by this, do these calculations, 1 upon z minus a upon z, z minus a upon z. Okay, z minus a upon z. Now see that denominator, this is the numerator, this is denominator, again this is denominator. Okay, that means numerator, denominator of a denominator, it become numerator, so we write this one as a z upon z minus a. Okay, this is the actual term we have to prove here. Okay guys, z upon z minus a, it is the expansion for z of a raised to k and k greater than 0. Okay, so whenever you have sequence, guys, whenever you have sequence z of a raised to k and k greater than 0, we can write z upon z minus a. And one more condition you need to know, that a need to be a smaller than z. Okay, and that means modulus of a z, it is a smaller than modulus of a. Okay, this term need to be smaller. Now in geometric progression we take this one is smaller. Okay, that condition I applied here. Okay, so I hope you all have understood this entire property. For your reference, you can take this note down. Okay, note it down for your reference. Just take the points, guys. Okay, so I'm gonna explain to you all next one example based on this first standard property. Okay, so here guys, I consider one example based on the above property. Okay, you will get at least a little bit conceptual idea after this example. Okay, which type of the examples are coming. Okay, so now see that we want the z transform of f of k, where f of k is a 4 raised to k and k greater than 0. Okay, now see that we have sequence 4 raised to k as a sequence, and we want the z transform of it. Okay, z transform of it. Okay, so we can write z transform of a raised to k. Okay, this one is our standard form. Okay, what is the standard sequence for z transform? We write the z transform of a raised to k and k greater than 0. K greater than 0, we write z upon z minus a. We write z upon z minus a. Okay, this one is our sequence. We write z upon z minus a. Okay, yes. So replace f of k as a 4 raised to k. So we write z of 4 raised to k. Okay, and k we have given condition bigger than 0, 0 or bigger than 0, greater than 0. Okay, so which can be written as z upon z minus, what is the value for a raised to k means 4 raised to k, a is a 4. Okay, now see that how easy I found the sequence z transform for 4 raised to k. Okay, how it is easier, just you need to know what is these results. Okay, so you can find this z transform directly using formula. Okay, not an issue, you can find out using this one, but I just save some of the step or timing that you can write directly z transform of the sequence like this way. Okay, yes, it is way easier guys, not the difficult. Okay, one of the easier concepts need to remember. Okay, yes, so need to replace the value and you'll get the answer in one step. Okay, this type of the questions are mostly important in your competitive exam. Okay, so if you know the result, you can solve this question easily. I hope guys you all have understood my today's lecture. It's one of the easy lecture guys, basic lecture, definition and some example based on the z transform. So even after if you found anything difficult guys, let me know in my comment section. I will come up with the similar videos. For recording one video, it is really time taking and challenging for us. Taking time for recording video, it's quite big hectic, but I'm doing it for you all guys as it is my passion. Okay, so please comment me in my comment section if you have any doubt, difficulty. So thank you everyone, thank you for my today's lecture.